Welcome to the solution to the Regents Physics Momentum problem set, problem number 19. A 30-kilogram gun is resting on a frictionless surface. The gun fires a 50 times 10 to the negative 3 kilogram bullet, that would be a 50-gram bullet, with a muzzle velocity of 310 meters per second. Calculate the recoil velocity of the gun after the bullet is fired. Calculate the kinetic energy of both the bullet and gun just after firing, and then determine was momentum conserved, was kinetic energy conserved, and explain. All right, with A, to calculate the recoil velocity, we are going to start by conserving momentum. Ignore this part over here. We'll talk about that in a moment. So we start with our conservation momentum statement, P before equals P after. What objects, if any, have momentum before the gun is fired? The answer is none of them, because neither one of them is moving. The gun itself is not moving. The bullet is not yet moving. So the momentum before is 0. Afterward, we have the momentum of the bullet at 50 times 10 to the negative 3 kilograms times 310 meters per second minus the momentum of the gun, 30 kilograms times VF. The bullet heads off in one direction and the gun recoils backward in the opposite direction. Therefore, we are subtracting the momentum of the gun. We add 30 VF to the other side, and then we solve for VF by multiplying and then dividing by 30. And you should get an answer, VF equals 0.517 meters per second. Note, an alternate here is that you could have said plus, but in doing that, your VF value would end up being negative, and that's okay also because that tells you the final velocity of the gun was in the opposite direction of the bullet. Either approach is fine. We're going to do part C now with this. Was momentum conserved? And the answer is yes. Momentum is always conserved, no matter the type of collision. In this case, you would consider this to be a reverse inelastic collision because the objects start stuck together and then go apart from each other. We've had other problems that you would say are elastic where the objects come together and stick together. We've had several of those. So this would be a reverse inelastic collision. A reverse inelastic collision. Part B, calculate the kinetic energy of both the bullet and the gun after firing. So we're going to do a separate calculation for both the bullet and the gun. So we write our KE equals 1/2 mv squared for both. For our bullet, our substitution will be 1/2 50 times 10 to the negative 3 kilograms times 310 meters per second. Don't forget to square. For our gun, KE equals 1/2 times 30 kilograms times 0.517 that we just calculated from part A, and don't forget to square. Calculating each kinetic energy for the bullet, we get 2,400 joules, 2.40 times 10 to the third, to the right number of sig figs. And for the gun, we get 4.01 joules. Well, was kinetic energy conserved? In order for kinetic energy to be conserved, these values would have to be equal to each other so that they cancel out and equal 0, which is the amount of kinetic energy before. So the answer is no, kinetic energy is not conserved. As soon as I described earlier that this collision is a reverse inelastic collision, that should make sense to you from the definition of elastic and inelastic, that for an elastic collision, both momentum and kinetic energy are conserved, but for an inelastic collision, momentum is conserved while kinetic energy is not. So as soon as you realize this is an inelastic collision, you already knew the answer to C for kinetic energy was no. All right, that'll do it for our discussion on problem 19. More to come as we tackle problem number 20 in class tomorrow.